Salmon is open source software that performs first principles calculations on the interaction between light and matter. In this video, we use Salmon with the acetylene molecule as an example to explain the calculation of the linear optical response of finite-sized materials such as molecules and nanostructures. This exercise is explained according to the manual on the Salmon website. You can access the Salmon website using this URL, https://salmon-tddft.jp. For this exercise, we assume that the ground state calculation of the acetylene molecule has been completed using Salmon. If you have not done so, perform the ground state calculations for the acetylene molecule. Please refer to Introduction to Salmon Execution Exercise 1 Ground State of Acetylene Molecule on the Documents page of the Salmon website for ground state calculation of the acetylene molecule using Salmon. Let us begin the exercise. Click the Use Salmon button on the left sidebar of the Salmon website to display the Salmon manual. Click the Exercises button on the left sidebar of the Salmon manual. On the left sidebar of the Salmon manual, click the C2H2 Isolated Molecules button that is below the Exercises button. Here we perform the calculation for Exercise 2 Polarizability and photoabsorption of C2H2 molecule. First, I will briefly explain polarizability, which characterizes the linear optical response of a molecule to weak light, and its method of calculation. The linear optical response of isolated finite-sized materials, such as molecules to weak light, is characterized by polarizability alpha. Polarizability alpha t is a function of time that associates the dipole moment pt, which is the coordinate of the center of gravity of an electron at a certain time t, multiplied by the charge E, with the electric field ET applied to the molecule. In general, it is the tensor quantity related to the x, y, and z components of the spatial directions. The polarizability alpha omega is a function of the frequency and is obtained by Fourier transformation of polarizability as a function of time. It is associated with various observables. For example, the photoabsorption cross-section sigma omega of a molecule for light with a frequency of omega is given by the imaginary part of the polarizability as shown in this equation. A quantity called the oscillator strength distribution dF d omega is also used as a dimensionless quantity that is different from the photoabsorption cross-section by a constant factor. In Salmon, polarizability is calculated by the following procedures. First, suppose that the ground state orbital function phi I is obtained using the density functional theory. For all the electrons contained in this molecule, an impulsive force of magnitude I is applied at time t equals 0 to accelerate the electrons. The orbital function immediately after application of the impulsive force is the orbital function phi I in its ground state multiplied by the plane wave exponential IIz. Using this as the initial condition, the time-dependent Kohn-Sham equation is solved. Then we determine the dipole moment pt by multiplying the coordinates of the center of gravity of the electron by the charge E. We can obtain the polarizability alpha omega as a function of the frequency by determining the Fourier transform of this dipole moment and dividing it by the magnitude I of the impulsive force. Now let us calculate the polarizability of the acetylene molecule using Salmon. It is assumed that the ground state calculation of the acetylene molecule has been completed in exercise 1. The files required for this calculation are contained in the salmon/exercise_02_C2H2_LR/directory. Let us copy the files to exc2 as the directory where the calculation is performed. C2H2_RT_response.inp is an input file. C_RPS.dat and H_RPS.dat are files of pseudopotentials of the carbon atom and hydrogen atom respectively. These were used in the ground state calculations. In addition to these, we require the results obtained from the ground state calculation. Suppose you perform ground state calculations in a directory called exc1. When the ground state calculations are completed, a directory called data_for_restart is created in that directory. It would contain data such as the orbital function of the ground state. Copy the directory as a whole to the exc2 directory and alter the directory name from data_for_restart to restart. Let us examine the contents of the input file C2H2_RT_pulse.inp. Most of the content is identical to that in the input file used to calculate the ground state. Here, we consider only the differences. In the first name list, calculation, the value of the keyword theory is tddft_response. This was DFT in the ground state calculations. The name lists system, pseudo, functional, and R-grid must have identical settings as in the ground state calculations. The name list T-grid specifies content related to time increments. dt specifies the time interval for calculating the time evolution of the wave function. Here, the time interval is 1.25 times 10 to the minus 3 fs. The unit is femtosecond, which is equal to 1.25 as attoseconds. Nt is the number of time steps in the time evolution calculation, which is 5,000 times here. That is, the time evolution calculation is performed for 6.25 femtosecond. EM field is a name list that specifies the electromagnetic field to be applied to the system. Equating AE underscore shape 1 to impulse specifies that an impulsive force, which is a momentary force, is applied at time t equals 0. EPDIR underscore RE1 1 to 3 specifies the direction in which the impulsive force is applied. In this case, because the x and y directions are 0 and the z direction is 1, the impulsive force is applied in the z direction. The namelist analysis specifies the information required to convert the dipole moment expressed as a function of time into a function of frequency using Fourier transform. The frequency is multiplied by Planck's constant, and the product is expressed in units of energy. dE is the energy interval, which is 0.01 eV here. N energy is the number of points of energy for which Fourier transformation is performed. Here, calculations are performed for 3000 points in increments of 0.01 eV. Thus, calculations are performed from 0 eV to 30 eV. Atomic underscore COOR is a name list that specifies the coordinates of atoms. However, this is also shared with the ground state calculations. Refer List of Input Keywords on the website for the name lists and keywords available in your input files. All the keywords are explained there. Let us perform the calculation. In the system used here, the command for MPI calculation is MPI-exec. Here, calculations are performed with the MPI process count as 2. When the calculation is completed, several output files would be generated. A sample output file can be downloaded from the Salmon website. Let us observe the contents of a few of these files. First, let us consider the standard output file C2H2 underscore RT underscore response.log. The first part of the file shows the version number of Salmon used in the calculation. Then, the input variables used in the calculation are displayed. When preparations for performing the calculation are complete, the time evolution calculation begins. The number of time evolution calculations is displayed in time step, and the time is displayed in time. The unit is femtoseconds. The x, y, z components of the dipole moment are written in units of angstrom. Electrons are the number of electrons calculated from the norm of the orbital function. The calculation algorithm does not stringently preserve the norm. Therefore, it starts at 10 and decreases marginally. Total energy, shown further to the right, is the total energy of the electronic system. After an impulsive force is applied at time t equals 0, no external force is applied. Thereby, the energy is conserved with high accuracy during the time evolution calculation. Finally, ITER-VH is the number of convergences of the conjugate gradient method performed each time to solve Poisson's equation. Let us discuss regarding the other output files. In C2H2 underscore RT dot data, the quantity obtained by the time evolution calculation is expressed as a function of time. Similar to the other files, the quantity that the file contains is described at the beginning of the file. The first column shows the time in femtoseconds, and the 17th to 19th columns show the x, y, and z components of the dipole moment. This is a graph drawn using the first and 19th columns. You can observe the oscillation of the dipole moment after the impulsive force is applied at time t equals 0. Next, let us consider C2H2 underscore response dot data. This file contains information regarding the time and frequency after the Fourier transformation. The first column contains energy in units of electron volts obtained by multiplying frequency by the Planck's constant. The second to fourth columns show the x, y, and z components of the real part of the polarizability alpha. Fifth to seventh columns show the x, y, and z components of the imaginary part of polarizability alpha, and the 8th to 10th columns show the x, y, and z components of the oscillator strength distribution proportional to the photoabsorption cross-section. This is a graph of the oscillator strength distribution drawn using the first and 10th columns. The oscillator strength distribution can be obtained over a wide range of energies from one-time evolution calculation. There is a large peak near 9.3 eV, which corresponds to the electronic excitation from HOMO to LUMO. C2H2 underscore RT underscore energy dot data contains the energy of the system as a function of time. In this calculation, energy is conserved because the external force is not at work after an external force is applied at time t equals 0. This concludes the explanation for exercise 2.